Hello, good morning, good afternoon, good evening. Thanks for joining this talk. My name is Stefan Winkler. I'm with the National University of Singapore and also AI Singapore. And today I'd like to share some of the work we've done on analyzing human emotions. Some of this work was done with my previous employers, University of Illinois and A*STAR, and that's why there's so many logos on this page. But let's get right into the topic. The motivation for this work is really that a lot of the current work on AI focuses very much on the IQ component of intelligence. It's all about analyzing data, better understanding data, finding correlations within data. But when we talk about human intelligence, a large portion of that is captured by what we call EQ, right? Our emotional quotient. So how we interact with people, how we feel, how we express those feelings, how we communicate those feelings. And that's what's really lacking in current AI systems. So if you look at existing agents like Amazon's Alexa, Apple Siri, other chatbots on the market, they're mostly voice-based, text-based. They will answer factual questions that you have, and they can also make some scripted jokes, but it doesn't go much beyond that. So for next generation agents, what I envisage is that they will really need to understand human behavior and human reactions. And this is, the first step, obviously. And then they also need to learn how to react appropriately to that human behavior. And that doesn't necessarily mean they have to react like a human, but appropriately for an agent, right? For an AI system. So this could be showing empathy or showing some type of reaction to that behavior. And that ultimately should lead to more natural interactions with those agents. So in terms of what I'm going to talk about today, of course, these are just small steps in that direction. I'll share first some of the project on photo work that we have done, where we use people-centric attributes for essentially managing personal photo libraries. And then that has actually led us to our current work on emotion recognition, which focuses mostly on facial expression analysis. And I'll talk about that as well. And then at the end, I'll give a bit of an outlook on the future work that I'm interested in. Now, photo work focuses on people-centric attributes. And you can see here some of the publications that we have written about this work. And I also talk about the motivation here. And this, for the past 10 or 15 years, or even longer, this hasn't changed much. The fact is that billions of pictures are taken every day. When I'm at a party or I go on vacation, then I myself take hundreds of pictures every day. And this massive flood of pictures is very hard to organize. And still, the tools available for that, even today, are not that great. There's a lot of tedious tasks if you want to create an album or share some photos, select some photos. And so the idea for this project was really, how can we make this easier? At least some of these tasks. And specifically what we focused on in this work was, what I share here, was automatic photo selection and sequencing. And this means essentially creating a pleasing slideshow. So imagine you have a personal photo collection, and I think that focus is quite important. A lot of work has been done on image retrieval for general image collections, but personal photo collections really highlights very specific requirements. And so there could still be many different people in that collection, different events, different locations, different dates, and so on. So we're going to extract all photos of a specific person or a specific group of people that we're interested in. Then we want to select the appealing, interesting photos that we would put in slideshow, and then also arrange them in an order that we find make sense for us. And that can then be used for sharing, or for printing, for showing, and so on. Now, there's three contributions to this work. One is a crowdsourcing study that we conducted to discover the user preferences. The second one is a dataset shaping technique to create a balanced dataset. And the third is a method to select and also to arrange those images into an appealing slideshow using the probabilistic knowledge gathered from the user study. So let me talk about the crowdsourcing study first. It had two steps. The first one was the selection step, and the second one was the sequencing step. So you can see the user interface that we had designed for the user study. So on the top left here, you see the image of the person that the album is about. And at the bottom, you see a few rows of images that are part of this album or part of this collection, and you are supposed to select those that you think are the best images or capture the best moments. And there's some instructions here, and also a space to leave comments on the selection process. And then you can, of course, click on the thumbnails, and you can see the images in more detail on the right here. Now, this was the first step. In the second step, the users were supposed to bring those images into an order that made sense to them. So the top was similar. We had, again, the person that the collection was about. And at the bottom, you could drag the thumbnails around and move them into the position that you preferred. And once you were done, you could then, again, leave comments and move on to the next task. Now, we had 5 different people-centric photo albums that we used in this study about male, female, about a couple, a girl, and a baby. They all had several hundreds of photos in them. And so we first applied our dataset shaping technique to obtain more balanced subsets with smaller numbers of images, more manageable for the user study. Now, to do this dataset shaping, we pre-selected some features that we thought would be of importance for making these decisions on selection and sequencing. And these attributes, we divided them into people-centric attributes and image-centric attributes. Now, the people-centric attributes, you can see them here at the top. They include how many faces there are in the picture, what is the size of these faces, the exposure, and also emotional components. So here you can see the first instances of this where we really thought that emotions might be an important aspect of this task. And then at the bottom half of this table, you see the image-centric attributes, which include things like scene type, sharpness, exposure. So all those traditional image attributes that you care about for image quality. Now, let me talk a little bit about the dataset shaping technique itself. The goal was to, as I said, to make these image sets a bit smaller for the workers to manage, and at the same time, reduce bias and maximize the diversity in the attributes and minimize the correlations between attributes. And the method we use for that is actually mixed integer linear programming. And you can, the details, you can refer to the paper for that, but you can see what the technique does. So here are some examples of distributions that may or may not be so desirable. So you can see here on the left, the data points are very well distributed, but if you select a subset according to the black dots, then you're left with a highly correlated subset or a subset that has high correlation between these two features, which may not be desirable. If you happen to look at the image B here, where we select those black dots, then of course, one of the dimensions is very underrepresented. So we don't cover the full range of this particular attribute, which is also undesirable. What we want is something closer to C, where we have uniform distribution. I mean, you can choose any distribution. You can choose Gaussian or Poisson, but typically this will be uniform distribution, or at least that's what we use for this particular study, uniform distribution across the attributes. Yet the correlation is still relatively high. And if you also impose the constraint that we want to minimize the correlation between attributes, you end up with something like what is shown in plot D here, where the correlation is close to 0, and we have uniform distributions across all the dimensions, all the attributes. And this is exactly what we want. So this is an interesting technique that can be applied to completely different problems as well, not just this particular data set or images for that matter. So it can be very useful if you have a highly skewed data set and want to create more balanced subsets. Now let's come back to the crowdsourcing study. We engaged close to 500 workers on Amazon Mechanical Turk. And if you've done crowdsourcing studies before, you know how important it is to screen those workers to make sure that what they deliver is actually based on the task you gave them, and them not just clicking randomly or making random selections. So we devised a method to compute a reliability score for each worker. And we used that to essentially decide which workers we had to reject and which workers we paid bonuses to. You can see some of the things that we used to do this. So for example, we had distractor images of a person that has nothing to do with the photo collection. And if those were selected, then of course it shows that these people were not paying attention to the task. We looked at how many comments they left, how much time they took, how much time they spent on the tasks, number of clicks, whether they were familiar with digital cameras and so on. So based on all these different components, we came up with the score. And then you can see what sort of the relative ranking of this score across different workers looks like. And you can see there's a lot of them that are about average. There are some of them, about 10%, which are who are a lot below average. Those were rejected. And then there's some of them that do a really nice job. Those are the positive outliers that we gave bonus payments to. Now, what we found from the results of this user study is that for these personal photo collections, the people-centric attributes have a large influence on the selection probability. And you can see that here as well. These plots show the marginal selection likelihood across the different albums in the study. And the first 7 attributes are the people-centric attributes. And then the remaining 6 are the image-centric attributes. And you can see that, for example, face count makes a big difference. So single images that contain a single face, a single person, are preferred over those of a group for this particular task. Close-ups are preferred over pictures taken from far away. Pictures with a good face exposure are preferred over those where the face is not well exposed. And again, this brings us back to the emotions. Emotions also play a role. So for example, positive expressions are preferred over those that are negative or neutral, but even negative expressions are preferred over neutral expressions, right? So you can see some of these people-centric or facial attributes do play a big role in the selection probability, how likely people are to select those images. Whereas, if you compare face exposure to generic image exposure, you can see that face exposure has a much bigger variation, right, as an attribute. Or generic image contrast, image sharpness, none of them have as much variability or influence on the selection as those facial attributes. So that was one of the interesting findings that, of course, applies to those personal photo collections and those albums specifically. Now that we have those probabilities from the user study, we can now use those probabilities in a prediction model. And this is exactly what we did. So you can see the results here. If we choose the images with the highest predicted selection probability, you get the set on the left here. If you choose the images with the lowest predicted selection probability, you get the images on the right here. And this corresponds very well to the discussion of attributes that I just went through on the previous slide. So well-exposed faces, close-up portrait shots are much preferred over distant group shots that are of not so high quality, which also makes sense. So this works relatively well, the selection probability for this model. What is a bit more difficult is the sequencing, but same thing, we can also use those probabilities that we found in the user study to build a model. So based on the probability of selecting a specific image for a given position in the slideshow, we can then work out these probabilities and maximize the overall probability for all the images in the slideshow. So it's essentially a combinatorial problem, that's how we phrased it at least, which we solved by integer linear programming. And again, for the details, I refer you to our paper. Here I'm just showing the high-level concepts behind what we did. Now, the interesting thing is that, of course, here we learned the probabilities for sort of the average user in that crowdsourcing study, but you can learn the probabilities for an individual, right? And then the output becomes personalized, right? So let's say for you specifically, colorfulness is a very important attribute. And then as we observe you manage your photo libraries, we can figure out that this is indeed one of the attributes that you pay a lot of attention to. And then we can adjust the probabilities in our model so that the slideshows and the selections we make can be personalized to your own tastes and preferences. So this is a nice feature of this particular approach. Now, how well does it work? So we did some benchmarking using album-based cross-validation for both selection and sequencing. And we compared against a greedy algorithm and also a regression-based approach. And the results are summarized in this table. I should highlight that this table is for image sequencing, which is the harder problem. So the selection results are actually a lot better, but the trends are similar. So I'm just showing one of the tables here. For the other table, again, you can refer to the paper. But what we found is that, of course, our method outperforms the others. That's almost a given. So that's the least interesting part of this table. But the interesting part is really that if we only consider image attributes, all of the methods, none of the methods perform very well. But if we add the people-centric attributes here to all of the methods, we get better results. And again, this is particularly true for our method proposed here, but it's also true for the other methods. And this again highlights the importance of those people-centric attributes. Now, as a final confirmation that what we were doing, our approach actually created meaningful and interesting slideshows, we did a user study based on the outputs of that algorithm. So we had a separate photo library with about 700 images, and we used that as input to 3 ways of creating a slideshow. One done manually by an expert, specifically the person who shot that photo library. One, a random selection and sequencing, and then the third one, our method. And so, granted, the random method, random selection is a relatively weak baseline, but this is what we had available. And then we also collected quality ratings of the resulting slideshows from 15 users. And we were happy to see that our method is significantly better than the random baseline for all these different slideshow lengths that we created. And it gets close to the expert slideshow in terms of user rating. So users had a hard time distinguishing the slideshow created by the person who took these photos from the slideshow created by our algorithm, whereas they didn't have any trouble doing so with the random baseline. So this shows that we're getting pretty close to human performance with our method already. All right, so much for the first part of the talk. Now I'd like to move on to the second part, which focuses on fine-grained facial expression analysis. Now, again, here are some of the references. You can also find them on my website, which I'll share later if you're interested to explore further. But now that, already in the photo work project, we found that emotions play an important role in terms of image attributes when we deal with these pictures. So now, can we take that to the next level, right? And the motivation for this is really that human emotions are mostly expressed by non-verbal cues. And so a large part of that is body language and the facial expressions, of course. There's voice tone, which also plays a big role, whereas words, meaning what we say, actually only plays a very minor role when we communicate our feelings and emotions. So we decided to focus more on those non-verbal cues, and because my background is computer vision, we focused on the face. We thought this was particularly interesting and relevant. Now, of course, emotion recognition has a relatively long history, but a lot of the work has focused on classification. So there's this 6 or 7 prototypical categories of emotions that many of the approaches rely on. And you can see them here. These include sad, happy, afraid, neutral. So they are very commonly used. But we found using just these categories has a lot of shortcomings. These categories work well when emotions are very intense, when the faces are very expressive, like actors can do perhaps, or you see in certain situations. But in real life, people do not display these very expressive faces. Expressions are much more subtle in real life most of the time. We don't burst into tears or burst into laughter on the street for no good reason. And then it becomes really difficult to classify these faces, these emotions, into a specific category. There's also variations in emotions that are very important. So for example, I like this example with the 2 babies here. Both show surprise in their faces, but one is positively surprised, the other one is negatively surprised. Now, if you classify them both into the same category, this may give the wrong impression, right? And may give the wrong analysis, because the meanings of these emotions can be very different. And so telling such emotions apart is also something that's quite difficult if you only have a few categories to slot the emotions into. And then finally, of course, we have those variations in intensity that we also want to capture, right? Makes a difference whether someone looks slightly happy or very happy. So all of this is relatively difficult to do if you only have a few categories. And a single label just does not reflect the complexity of human emotions. So we decided to follow a different approach, which is the emotion continuum. And there are a few different ways, a few different models for this. We picked the circumplex model that was introduced by Russell in the 80s, based on emotional words. And essentially, Russell designed this continuous space with 2 dimensions. One is called valence, which separates the negative from the positive emotions. And the other one is called arousal, which distinguishes passive expressions versus active expressions. So these are the 2 main dimensions of this space. The nice other feature is that the intensity is essentially represented by the distance from neutral, which is in the middle of this circle here. So here I have neutral emotions, and then as you go more towards the perimeter of the circle, you have higher intensity emotions. So we decided to use this emotion representation and then try to apply this to facial expressions. And so here you can see what happens when we do this. So again, in the middle of the circle, you see a neutral face. And then as you go towards the edge of the circle, the emotions become more intense. So we go from neutral to slightly happy to very happy. So happy, you can still have categories, you can still assign categories to different parts of this circle if you want to assign labels. But the nice thing is that now these are continuous numbers, and you can actually work with the numbers directly. And so we designed a mapping that allows us to go from facial expressions to different points on this arousal valence plane. And doing that, of course, is no longer classification. We chose a regression approach to do so. And that has certain advantages, as I'll show you in the remainder of the presentation. We developed different methods to essentially do this mapping. One is based on partial least squares from 49 facial feature points. So this then follows traditional face detection, facial feature point detection and tracking. We estimate the head pose, we frontalize the face, and then from that frontalized face, we're able to measure arousal, valence, and intensity. We also implemented a deep learning-based approach using multitask CNN design, where face detection and the emotion recognition essentially is done concurrently in the same network. Now, the tricky part when we started this work, most of the data sets only had categorical labels. So we were not able to train our model. So we came up with this approach that we call MorphSet to augment the existing data sets that only had categories, and to create arousal valence annotations based on those data sets. So essentially, this was an augmentation approach based on morphing images between, let's say, a neutral face and a happy face, right? And so you can slowly morph and interpolate the different expressions along this line with different intensities of the same emotion. And what we also did was interpolate between different emotion categories. So for example, surprise is approximately here, whereas happy face is approximately here. And then we can interpolate different mixed emotions between those two using our face morphing. And this worked surprisingly well, actually. We found the images to be very convincing, to look very convincing and very realistic. And so we decided to use this as our training data set. We're able to, again, come up with a very balanced data set, create a lot of training examples from a single person using these particular data sets as the base. And then this MorphSet, indeed, we get pretty good results when we train our different methods, the CNN or partially squares on it. And this also compares favorably with other data sets. Meanwhile, there's a couple of other data sets that also provide arousal valence labels. One of them is EffectNet here. And you can see that our methods also perform on a similar level or somewhat better than what's used in EffectNet, for example. So that's nice, but maybe just to show you some examples of the real advantages of this continuous circumplex model that we use for emotional representation is when we compare classification in discrete categories to a continuous approach. So the discrete categories here are shown on the gray box, where you have the 7 different categories. It's a bit small, but what you see here is that the neutral category is at 100% for each of these images. So the yellow bar indicates this 100% neutral for each of these 4 faces. I can argue whether these faces should be categorized as 100% neutral or something else, but certainly they shouldn't be categorized as the same expression, the same emotion, right? Because they all show relatively strong differences, in fact. And now we can look at the output of our method, which is shown in the arousal valence space, indicated by the circle here. And the red dot shows the arousal valence computed by our method. And you can see that the red dot is not only away from neutral for each of these images, so it's away from the center of the circle, it's also in a different position for each of these images. So that means that using our approach with a mapping regression approach to a continuous emotion space, we are actually able to tell these faces apart in terms of the expressions and emotions. And this is, much more powerful than just saying each of these faces is a neutral face. Now, let me show you an example of how this works in a sort of a live demo that we've developed. So here can sort of load up a video, and you can see how the face is detected, how we detect certain feature points on the face, around the eyes and the mouth, which are of course the expressive parts of the face. And then as we have, as we do the analysis, and here we just focus on a single face, the largest face in the video, we can do the mapping onto the arousal valence space, and the output of this is shown here on the right. You can see that it's very responsive, so it reacts immediately to even small changes in expression in the face of the person. And then, of course, down here we can look at different graphs and statistics of the measurements. Now, where it gets even more interesting is when we look at multiple faces. And so here's an example of this. Here, this is from a talk show where we have many people in the audience. And you can see many of these faces are actually very small or in a side view. So sometimes we're not even able to detect them, or it's very hard to analyze them. And so the measurements, of course, become very noisy. And you can see that the blue dots here are a little bit all over the place, because everybody's expression is different, and because of the challenging conditions here. But what's more useful than the individual faces in this case is the average of all these emotions, which is also much more straightforward to compute if you have continuous emotion representation like valence arousal numbers. And so this is indicated by the red dot here. And you can see that is much more stable. So we're now able to capture the mood of a crowd in a given room or environment by looking at many people at the same time. And then that mood really becomes a useful measurement for the emotional state of a group of people in a certain place. Let me talk about some applications of this, some use cases, which I find quite interesting. One is comparing individuals. And here's an example from the previous presidential debates, Trump versus Clinton. So we looked at both candidates and analyzed them with our tool. And then we plotted heat maps for each of them taken from the debates. And you can see this is the output essentially. And we can see quite stark differences in the heat maps here, right? You can see that Trump mostly is in negative territory for valence, so mostly shows negative expressions, hardly smiles, hardly engages positively with the audience. Whereas Clinton is very different. Her face is mostly neutral during the debate, and then she also smiles, laughs a lot more than Trump does. So it's a very different behavior style and interview style. And this is what we can now objectively distinguish using our measurements. And you can imagine using this in sort of assessment situations for, let's say, certain mental conditions, or in interviews where you might want to have objective assessment of how people behave, how people respond to questions, just based on their facial expressions. Now, the second use case is related to crowds. And so here we actually captured faces in a local MRT station, subway station, over a couple of weeks. And then we just plotted the heat map of all the faces we captured. So this is many, many different individuals. And then we can capture the overall mood, as I said, of this crowd in this particular space. What you see here is that MRT stations, subway stations are not necessarily a happy space, not even in Singapore. So people are rushing to work or back home, and of course they're a little bit frustrated or stressed because of whatever reason. And now this is useful overall. Of course, we already expected that, we already knew that, but we can use that as an objective baseline for the mood in this particular place. And now we can make changes to the space. We can introduce better crowd control, higher train frequency, better lighting, nicer music, whatever it may be. And then we can run these measurements again and see if the mood of the crowd has improved as a result of the changes that we make to the space. So having these objective measurement tools of crowd mood or individuals' emotions can be very useful in such situations. Now with that, let me come to sort of the end of the description of those two projects. Just to summarize what I've talked about here so far, the first part was about managing personal photo libraries. And we saw that people-centric attributes, including and in particular emotions, play a critical role for that problem already. And then we focused more on the emotion analysis, and I showed some of the fine-grained emotion analysis we are able to do using a dimensional representation of emotions, using regression rather than a classification approaches, which allows us to better capture subtle expressions and small variations in emotions. Now, before I end, let me just say a few words about what's next. Now, of course, this comes back to what I said at the beginning. What was the motivation for this work? Is really that helping systems, agents become better at understanding, at interpreting human behavior, and emotions are a big part of that. Now, of course, that's still a long way off, but there's some intermediate steps we can take. One is the personalization of emotion analysis. We haven't spent a lot of time on that yet, but I highlighted some of the possibilities along the way for both the photo work and also, of course, for understanding individuals' emotions. Let's say longitudinal studies of how a person's mood changes throughout the year, or things like that. We only looked at facial expressions, but emotion is really a multimodal problem. We need to consider speech, we need to consider voice, tone, gestures, posture, the context, the interaction that takes place to really have a reliable understanding of this. And then one of the issues that I've also highlighted is data, right? So data for emotions is particularly tricky to collect. And so I think this is one of the areas where data augmentation is important. It's an important tool to use. Nowadays, we have very powerful GANs that are able to help us with that for augmentation. So we also spend some time on developing methods to train GANs more effectively, use GANs to discover commonalities, particularities of distributions. So you can refer to some of the papers on my homepage if you want to learn more about those applications and the work on GANs. And so let me just, at the final slide, come back to the overall problem, which is really multimodal behavior understanding, right? So we have different attributes that we want to understand, be it age, gender, ethnicity, personality, which are, of course, relatively permanent attributes. And then we have the more transient attributes that we talked about, like affect or mood, engagement, fatigue, frustration. All of these, whether they're directly related to emotions or not, can be of interest. Then we have various cues we can use to understand them, appearance-based cues, which are generally easy to collect, other cues that require more intrusive or physiological sensors, which are a little bit harder sometimes. And of course, the data, how do we get the annotations? How can we augment these data sets, maybe generate them synthetically? This is also still a big question. And a lot of the data sets that we've seen for emotions are actually very, very noisy. And so the performance we can achieve on them is actually not very high, and is partly due to the noise in the data. And once we made some progress here, there's lots of interesting applications that we're already looking at with a startup that I co-founded actually. So we can look at retail experience, healthcare, education, robotics, personalization of systems, all because we can better understand human emotions, human behavior. And I don't think this can be done by engineers, computer scientists alone. We also need to collaborate with psychologists, social scientists to help us understand that and model that better. So let me end here. Just a thank you slide at the end. Thank you, the audience, for listening in. Thank you to my team who has worked on this with me over the years. And as I said, if you'd like more information, please go to my website, which is listed here at the bottom. You can also check out what we do at Opsys, the startup, and feel free to drop me an email if you have any specific questions. Thank you very much.